Okay, in this video we'll be discussing the idea of impulse. You might have heard impulse being described as the change in momentum. In order to get the change of momentum, we can take the momentum finally and minus it from the momentum initially. And therefore, as we know, P is equal to mv. In order to get the change in momentum, we can take the mass times the velocity finally minus the mass of the velocity initially. Now from this, we can see that impulse is related to force. This is because one of the definitions for force is that force is the rate of change of momentum. And therefore, from this definition, we can say that force is equal to the change in momentum over time, right? The rate of change of momentum, so we have the change of momentum over time. And therefore, we get delta P is equal to F times T, which this is the impulse equation that you're probably familiar with. One of the scenarios in which we'll use impulse in level 3 is, let's say we have a 5 kg ball and it's moving off at 3 meters per second and it's about to collide with a 2 kg ball. Now after the collision, the 5 kg ball moves off in this direction at 2 meters per second and the 2 kg ball moves down this way at a velocity which is unknown. And for trigonometry purposes, we have a right angle right here. And in this scenario, we want to find the force experienced by 2 kg mass after being hit by 5 kg mass. So in order to solve this, we first need to get our vector triangle. We know that initially the 5 kg mass was the only object with momentum because the 2 kg mass was stationary initially, right? We can see that up here. And so therefore we can draw that vector right here. We know that afterwards the 5 kg mass goes up in the northwest direction. So we can draw that vector right here. And we know the 2 kg mass comes down in this direction right here. So we can also draw that vector down like that. Now we also know that momentum is equal to mass times velocity, and therefore the momentum initially of the 5 kg mass is equal to its velocity, which is 3 meters per second, times its mass, which is 5 kgs, which we know is 15 kg meters per second, right? Now for the 5 kg mass afterwards, it has a velocity of 2 meters per second, and its mass still remains the same as 5 kgs. And so therefore its momentum is 10 kgs meters per second, right? Now, for the 2 kg mass afterwards, we can't find its momentum because we do not know its velocity. And so therefore, that remains unknown. However, due to this geometry right here, we know that that must be a right angle between them, right? We see that from here. And so therefore, as we have a right angle, we can use Pythagoras. So we know that Pythagoras is a squared plus b squared is equal to c squared. As this is our hypotenuse, we can label this our c, this can be our a, and this can be our b side. And therefore we want to rearrange this for b, and so therefore b squared is equal to c squared minus a squared. Now to remove the lettering, we can call this b our p2, right, momentum of the 2 kg mass. And so therefore our p2 squared is equal to 15 squared minus 10 squared. And therefore, our P2 is equal to the square root of 15 squared minus 10 squared. And this gives us a momentum of the 2 kg mass as 11.18 kg meters per second. Now we are not quite done yet. We have found the momentum, but we have not found its change in momentum. So we know that the change of momentum is equal to the momentum finally minus the momentum initially. And therefore the change of momentum is equal to 11.18 minus its momentum initially, which was 0 because it was stationary. And therefore the change in momentum is indeed 11.18 kg meters per second. Now in that case, that step was redundant, but there might be a case where it isn't redundant and the 2 kg mass actually might have an initial momentum that you would have to minus off. So now we know that F is equal to the change in momentum all over time. If we set the time for this collision as 0.04 seconds. We can therefore say that the average force is equal to 11.18 all over 0.04 seconds, and therefore the force experienced by the 2 kg mass is 280 newtons. And there we go, that's our final answer. However, if we change this time to 0.08 seconds, so now we have doubled the time of the collision, and this can be done with padding of any kind, right? If we add some extra padding, now this working is now redundant, and so we can go again and say that the average force is again equal to the change of momentum over time, and therefore the force is equal to 11.18 as the momentum does not change from previously, and that's all over our new time, which is 0.08. And that gives us a force of 140 newtons. And so as you can see, if we add some padding and therefore extending the duration of the collision, the force experienced by the object is decreased. Now this is important for things such as safety, in terms of, let's say in a car for a seatbelt or airbags. What those things do is they increase the duration of the collision. And so that's important because if you're in a car crash, you want to survive, right? And in order to do that, you need to reduce the force experienced by the person in the car. And so this concept comes up quite frequently in an excellence question in terms of a written question. I need to discuss how increasing the time of a collision will result in less force experienced by the person in the car or whatever. Wearing a helmet, same thing. And so you can relate it back to this equation right here in your discussion. Okay, that is all you need to know for impulse and level 3 mechanics. Sweet as.